Hello everyone. In this video we are trying to solve the following problem. This is also a distribution of charge. So in this video, or in this question I should say, we have a line of positive charge is formed into a semicircle of radius r, 60 centimeters as shown in the figure. The charge per unit length along the semicircle is given by the following expression. So lambda is equal to lambda naught cosine theta. This indicates that the charge is not uniformly distributed, because if you think about the equation, you have cosine theta. Theta is the angle between the y-axis and a part or a point on the charge. So we see if you go this way, theta increase. If you go that way to the left, theta decrease. Actually, theta is between 0 to pi over 2 and 0 to minus pi over 2. So theta in this question is between minus pi over 2 to plus pi over 2. This means that the charge is more accumulated. So if we assume that charge is positive, so charge is more accumulated here and then get less and less while you go away from the center. So almost at the end point here and here, there is no charge. Okay, so this is the meaning of it. So the charge is not uniformly distributed along the semicircular shape. The total charge of the semicircle is 12 microcoulomb. So this is the charge of this shape. Let's call it Q uppercase Q. The question asks for calculate the total force on a charge of 3 microcoulomb placed at the center of the curvature point P. So we have another charge. Let's call this charge small q. So first of all, why there is a force if you bring a charge and you place it over here? The answer is the semicircular shape will produce an electric field at point P. So according to this equation, a force equal to Q multiplied by E. So the electric field is from the positive charge, from the semicircular shape, and Q is the 3 microcoulomb. So this should be our starting point to solve the problem. But we have other problem we need to get rid of it first. So if you look at this equation, lambda naught is not something that given. So we know R, we know total Q, we know small q, we know theta from minus pi over 2 to pi over 2, but we don't know lambda naught. So first we need to get rid, or we need to find lambda naught. So from definition of lambda, I could say, so lambda is equal to dq divided by ds. ds here, it's a length of a small points on the wire. So that small points that is shown here, I'm going to magnify it. So that small piece here, I'm going to magnify here. So this, I'm going to just draw it like that. So this is ds, right? This is r. Let's call this one d theta. So now we say ds is equal to r d theta. Okay. So that simply tells me that dq is equal to lambda ds, but our lambda is lambda naught cosine theta, and our ds is r d theta, right? So in order to find lambda naught, we need to do the integration of this. Okay. So integration of the left hand side simply going to give us total q. This is the 12 microcoulomb, right? Equal to lambda naught constant, r is constant, integration of cosine d theta is equal to sine theta. But from beginning we mentioned that theta changed from minus pi over 2 to plus pi over 2. Okay, so it's from minus pi over 2 to plus pi over 2. And this is basically is equal to 2. So that means that Q is equal to lambda naught r, actually maybe just 2 here, right? So lambda naught is equal to Q divided by 2R, which this easy to be found because we have all the parameters. So Q is equal to 12, 10 to the power minus 6, 2, and our R is 60, so it's 0.6, and this simply equals, so this equal to 6, this is 1, this goes with that, so this is 10 microcoulomb. Sorry, 10 microcoulomb divided by meter, so it's 10 to the power minus 6. The unit of linear charge density is simply coulomb divided by meter. So we know that lambda is equal to lambda naught, which is this number, cosine theta. Okay, so this is this parameter. Okay, this is this parameter or this expression. Now it's time to move on and try to find the electric field at point P from the semicircle. So this is our second step. Okay, this is our second step. Okay, now it's time to calculate the force affecting on a charge 3 microcoulomb if that charge is placed at the point P. So this is the charge Q. Now what happens if this charge was located at point P? Of course, this charge will be affected by a force according to the following equation. F is equal to Q multiplied by electric field. Now electric field is the electric field at point P produced by the semicircle because it's charged, right? So now our job is to find the electric field at point P. So to do that, because the semicircle is charged and it's a distribution of charge, we need to divide this into many small pieces. So let's say this is one piece, this is the second one, this is the third. So it's many small pieces, right? So the first piece, so we divide the charge into many small pieces. The first piece, let's say located here at theta equal to minus pi over 2. The last one at theta is equal to plus pi over 2. So let's select this small piece. It carries a charge dq and it has a length of, let's call it ds. Okay. As if we assume the charge is positive, so that small piece dq will produce electric field at point P direct diagonally this way. Let's call it dE. This electric field vector has two components. One goes down, let's call it DEY, and one goes to the left, let's call it DEX. Okay. This is our theta, so this is the same theta. Right? So now DEY is equal to dE multiplied by cosine theta, right? Cosine theta, and DEX is equal to dE sine theta. Okay. Now you have, of course, this is for one component, right? So you have too many DEX and you have too many DEYs, because this is not the only piece on the semicircle. You have too many of them. For example, for every small point on the right side of the y-axis, there is a point corresponding to it on the left side of the wire. So for example, for the DQ shown here, the yellow highlighted piece, there is another piece located on the left hand side. The electric field from this piece, from the left one, also goes diagonally this direction, which has two components. One component will be to the positive x-axis, and one component will be to the lower, or let's say the y-axis, negative y-axis. So you see that the x component, positive x component, will be cancelled with the negative x component. So you could do that for any 2 points to the right or to the left of the wire. So by definition, because of symmetry, we say that if we do the integration of dEx, if we add, integration simply is addition, right? Addition of all these components simply is going to be equal to 0. We say it by symmetry. We could actually even prove it mathematically, right? We could do this integration and the integration limits from minus pi over 2 to plus pi over 2, and we should be able to prove that it's equal to 0. But we don't have to do it mathematically. We just say by symmetry the addition or the integration of dx simply goes to 0, which means the electric field at point P simply is equal to integration of dEy, which equals to dE is equal to k dq divided by r squared, right? And multiplied by cosine theta. Okay, now let's do something for this dq. So dq we know is equal to lambda ds, but our lambda is lambda naught cosine theta, and we know the value of lambda naught, so it's equal to lambda naught cosine theta. So dq is equal to lambda multiplied by ds, so this is lambda, ds is equal to r d theta. I'm going to write r here, and I'm going to write d theta here. So we need to use this over here. Remember, we have cosine theta, there is another cosine theta, so it's going to be equal to cosine square theta. So electric field at point P will be equal to, now I'm trying to bring the constant outside. Remember, there is r here, there is r square here, one of them will be cancelled out, so it's going to be equal to k divided by r, what else, lambda naught integration of cosine squared theta from minus pi over 2 to plus pi over 2, right, d theta. Okay, so we simply need to find this integration. So we could use the identity, well, cosine theta squared, we could write it in the following way. So this equal to k lambda naught divided by r integration of 1 over 2 plus I think sine 1 over 2 again, sine 2 theta d theta. Okay. Actually, this is, I did a mistake. This is cosine 2 theta, not sine. This is cosine 2 theta. Cosine 2 theta. And of course, the integration is from pi over 2, minus pi over 2 to plus pi over 2. Okay, this is not difficult. The answer for this simply, the first term is equal to half theta plus, and the second term is simply 1 divided by 4 sine 2 theta. And of course, we have to put the limit of integration plus pi over 2. This basically is equal to pi over 2. So the final answer for the electric field at point P will be equal to k lambda naught divided by r pi over 2. So we need to do one more step, which simply using that equation, right? So the final answer, the force that will be affected on the 3 microcoulomb charge, if it was placed at point P, simply equal to Q multiplied by electric field at point P. Okay. So F is equal to K lambda naught Q divided by R pi over 2. Okay, I'm gonna skip the last step, which basically substituting all this by numbers, by the number that are given here. Remember, we've already found lambda naught, and then of course you're gonna get the numerical value for the force in Newton. Okay, that's it. I hope my video is clear, and thank you for watching.